molecules. Please go ahead.
All right, thank you very much. So it's a pleasure to virtually be there on the other side of Germany. As I checked, this is the only Glueball talk that, well, it's theoretical Glueball talk that we'll hear at this workshop. This is not the usual Glueball talk. This is a talk about Glueball molecules. So what they are, I'll tell you in just a second. So as we know, quantum chromodynamics is simple, at least according to Frank Wilczek, who talked about that in Physics Today back in 2000s. That's it. That's the Lagrangian as we know. It's very simple. It involves glue fields and quark fields. So everything is easy. Well, maybe it's not so simple. Of course, as we know, QCD Lagrangian is written in terms of wrong degrees of freedom. So what we see experimentally are mesons, baryons, and other degrees of freedom, not quarks and gluons. So since gluons can carry color charge, they can self-interact. So the question is, can there be bound states of pure glue? And so this curious fact that we can form colorless combination of glue fields is that there's a curious fact about that the Higgs field, which has to do a little bit with the mass of every other particle that we know, has absolutely nothing to do with the mass of the glue balls. That's a pure QCD effect. Even protons have a small contribution from the Higgs, but glue balls, pure QCD. So the question is that if, in principle, glue balls can exist, can we predict their spectrum? So, of course, in quark models, we knew how to predict spectrum of various states because we could model them in terms of potential between quark and anti-quark states. So, quark-anti-quark potential gives us a spectrum of the usual QQ bar states. It is, however, not so easy to do for gluons, and it has to do with gauge invariance. Although people have attempted to do that, there are constituent glue models, there are flux tube models, bag models, and so on and so forth. There are various predictions for the spectrum of glue balls, different quantum numbers. And of course, the only surefire thing that we can say right now is that since gluons have a spin one particles, all glue balls should be bosons. There are no baryon type of particles among them. So there are various methods that were employed to predict the spectrum of glue balls, lattice QCD sum rules, everything. And it's sort of broadly given in this slide over here. There are some old predictions of a lattice with a quenched spectrum, which we should probably not believe, the quench approximation, or some model dependent or model independent predictions from more modern methods, including the lattice. And the only lesson that we should take from here is that the lightest possible state that is predicted by all methods is the 0++ state. There are others that are much heavier. For instance, 1 - state is almost as heavy as a J psi. So before we proceed, I want to make a statement about how glue balls behave at large NC. So the question, if we are to see a glue ball state, do we expect wide or narrow states? Well, it is difficult to say model dependently, but however, there are lots of model dependent results. Maybe large NC counting rules can provide some guidance. And so in a 't Hooft limit of large NC, where each coupling goes like 1/√NC and each quark loop counts as NC, one could say that the widths of glue balls behave like 1/NC, whereas the widths of a QQ bar states behave like 1/√NC. So glue balls actually narrow in the large NC limit, so we should expect smaller widths. Of course, this is a large NC argument that doesn't mean anything. It shouldn't. It might not even hold in real life. Nevertheless, there is some guidance from at least some theoretical limit that we could use later on. So as I said, experimentally, there have been so many different searches for glueballs, but it still appears from theoretical predictions that the 0++ is the lightest possible glueball state. And so one can base the searches on that fact. So it must be produced copiously in a glue-rich environment, and it couples strongly to the color singlet digluon state. So for instance, one can possibly see it in radiative J-side case. Its production in gamma-gamma collisions must be suppressed simply because glues don't carry electric charge. And the decay of production amplitude for glueball is flavor independent. At least that's what should we expect. And it must be narrow. There are, as I said, there are arguments stemming from the large NC limit, but there are also chiral arguments, as this paper from Chanovitz. So while this is specifically true for 0++ glueball state, it is generally true for other glueball state as well, maybe except for searching for things in the radiative J-side case. And so, of course, experimental searches are easy. You just have to Google search it, and you will find actually that there are glueball making machines on the market. You can actually buy them for cheap. Now, of course, real searches are done at general purpose experiments, and not just general purpose, but also, specific experiments such as GlueX. And after all that I told you, that glueballs could be narrow, they are produced in a glue-rich environment. So far, there is no convincing observation of a glueball state yet. Why is that? Well, the reason for that is quantum mechanics, basically. So as we could see, glueballs and QQ bar states might have the same quantum numbers. So I told you that the latest glueball state has a quantum numbers of 0++, but there are also QQ bar states that have the same quantum numbers. So quantum mechanics actually requires mixing of those states, especially if they are in a region where their masses are close together. So that actually means that the pure glueballs do not exist. Unless there is a reason for that. So every time we are talking about glueball, we are talking about a part of the meson wave function that pertains to glueball state. And so there have been a number of studies, if you concentrate on 0++ states, of trying to see admixtures of pure glue into the wave functions of F0 states that have exactly the same quantum numbers. And so experimentally, there are many different fits, and at least some of the studies from, let's say, 2015 assume that it is the state of a 1710 F0 that contains the most of a glue, so it's almost a pure glueball. In this talk, so while this is known, it's been known for years. In this talk, I would like to propose another mechanism for glueball hadronization. So we know from this conference, from the discussions in this conference, that there are many candidates of meson-meson or meson-baryon molecular states. So on the general grounds, one might ask, why not glueball meson or glueball baryon molecular states? The glueballs have smaller widths than mesons in a large NC limit. So that fact might actually have some implication for some unusual properties of observed highly excited states. And what do I mean by that? Well, so if you have a situation where a glueball meson state has a somewhat small binding energy, one would expect that that the states of the quantum numbers, such as, for instance, 0 minus plus, pi and 1800, would have a somewhat significant contribution from such molecular state. So another thing is that if I once again take the lightest 1 minus glueball, and try to find a bound state, a molecular bound state between this state and a pion, so the lightest molecular state like that, we would find that the quantum numbers would be would be the same as the quantum numbers of X3872, which might lead to quite unusual conclusion that the part of the X3872 wave function does not contain any charm. So that would be an interesting thing to check. So in order to, so those are the assumptions, right? So the question now is that, can we have such molecular states? And so for that, I would need to find a theoretical description that is suitable for building Glueball meson molecular states. So fortunately enough, states like that have been described successfully. And an example is a description of X3872, which, back even when it was discovered was had universal properties. We knew if with a state with large scattering length, it has a wave function that is essentially determined by quantum mechanics, and one can build that particular wave function using chiral arguments, as for instance we did as a molecule of D and D star. So in this case, I can do exactly the same. I can build a molecular state between a pion and a glueball if I knew how to describe glueballs and pions in effective field theory. So what would I expect from such a state? But the lifetime of the state would be governed by the lifetime of its glueball component, because as far as the QCD is concerned, pion is a stable state. So that means that for a heavy state such as this bound state, well, presumably 1800 MeV, I would have smaller widths, at least from the large NC argument. So it possibly will have large mixing with highly excited QQ-bar states. The argument here goes that the molecular state, the size of that state is governed essentially by the inverse binding energy, and the highly excited QQ-bar states, their sizes are inverse lambda QCD essentially. So what we should expect is somewhat unusually long-lived, highly excited states. So this particular state can also be alternatively viewed as a Glueball excitation of a state of a pion. And the lightest state that we'll try to describe is a 0 minus plus or pseudo Glueball state, well, because it has a pseudo pseudoscalar quantum numbers. So let's build this state. So it's sufficient to have an effective description of 0 plus plus Glueball, and this is possible to do so using the fact that in a massless QCD limit, QCD is classically invariant under dilatations. So this symmetry is broken at the quantum level, and in particular by gluon condensates. And so one can effectively describe excitations of that state as a scalar dilaton field described in the trace anomaly. So this description of a 0 plus plus Glueball fields has been known for years. In particular, I think the last paper where it was described was in the 80s by Migdal and Schiffman. And so this particular Lagrangian describes a dynamical degree of freedom, which is a dilaton field, which has the same quantum numbers as a 0 plus plus Glueball, which is described by this effective Lagrangian. This effective Lagrangian has a minimum, and the excitation about that minimum is indeed a Glueball. So we also need to couple pions and glueballs, and so to do that, there are already works that couple mesons and glueballs, in particular from the work of Janowski and company. They use the linear sigma model to couple scalar fields to the Glueball field, which is described by the dilaton, in order to study mixing between the QQ-bar states that are effectively given by the fields in this model and the Glueball state. So the phi over here in this Lagrangian of a linear sigma model is given by the scalar part over here. So the sigma is the scalar state. Eta sub n is a strange less component of the eta state, and the pion, the octet of the triplet of pions is given over here. So if we do just like what we usually do in the linear sigma model, we can expand this this Lagrangian in terms of the fields and determine interactions between the pions and sigmas and so on and so forth. So in order to determine what is interesting is that the same Lagrangian, you don't need to add any new couplings to it. The same Lagrangian contains the interaction term, which has an interaction of a Glueball field and the states of pions and sigmas. So it is the same interaction Lagrangian that describes the mixing of scalar particles, scalar QQ states, and the Glueballs that was employed in this paper and others in order to describe the mixing of Glueballs with QQ states. It is exactly the same Lagrangian that describes Glueball molecules. So in a small momentum transfer, we have to match all possible interactions of Glueballs with pions to determine the pi Glueball coupling. So we can match to non-relativistic effective field theories for pions and Glueballs. So to do that, we can expand the glue field and the sigma field about the minima. So this would give us an interaction piece that describes interaction of glue fields and a sigma. This piece describes interactions of sigmas and two pions. And there is a piece that comes directly from this Lagrangian that describes interactions of pions and the Glueballs. So altogether, we can match it to a non-relativistic effective Lagrangian describing interactions of two pions and two Glueballs with a coupling constant over here, which is given by this. So those are parameters of the linear sigma model. This is a parameter of the interaction that was given previously to describe mixing between Glueballs and QQ bar states. So there are no new couplings required. This is all given over here. So now we can see if there is actually a molecular state in the spectrum by calculating a low energy pi G scattering amplitude and looking for a pole in the amplitude. So the pole of the amplitude corresponds to the bound state, and the energy of the pole can be read off that particular thing. So as we know in quantum mechanics, we can calculate binding energy from the pole of the transition amplitude, right? So this is the transition amplitude in quantum mechanics, and so the pole over here describes the state that the non-perturbative state. So in quantum field theory, we do quite a similar thing. We have to solve a Lippmann-Schwinger equation to find a total transition amplitude. So the Lippmann-Schwinger equation is well known, and it's given graphically by this. So this is totally equivalent to resumming the bubble graphs that people do in field theoretical descriptions of deuteron, started by Steven Weinberg and continued by KSW and KSW scheme. So here the situation is somewhat easier. So the Lippmann-Schwinger equation is given over here. So this Lippmann-Schwinger equation could be solved, and the solution of that equation is given over here. So a tilde over here is an integral that is given by this one loop amplitude. And just like in the case of deuteron, we would expect that this integral is divergent. We can take an integral over Q naught over energy. And so what we would be left with is an integral in 3 dimensions, which actually contains an inference singularity. This is something to be expected because one cannot build a bound state simply perturbatively. So it's the perturbation theory here tells us that there's got to be a singularity. The situation is exactly similar in when you try to build a hydrogen state in QED, or if you try to build a deuterium state in effective field theory that is describing interactions of protons and neutrons. So the solution is known for that. So we would have to renormalize. We would have to subtract the divergence by renormalizing this coupling constant that I introduced before. So this approach is very similar to the Weinberg's treatment of a deuteron. And so a solution here tells me that there is indeed a pole in the scattering amplitude, and that pole corresponds to a state with a binding energy that is given over here. So it's a bound state energy of about several MeV. So this is amazing.
5 minutes left.
Yes, I'm almost there. So if you now see around for a possible state that might fit the description, let me just show one of the transparencies showed by Paul Eugenio back in 2016 at the APS April meeting. So the pi in 1800 has been a somewhat puzzling state for a while now. So it is rather narrow for a second excitation of the pion, does not decay to rho pi or kk star, and so many suggested that this particular state is a hybrid meson. So, for instance, given in this classic paper over here. So what I would suggest is that a pion 1800 is in fact a Glueball molecule. That is to say, it contains a dominant part of the wave function is built from the Glueball pi molecular state. And so the lifetime of this molecule is driven by a Glueball lifetime. So it is rather narrow, at least in the large NC limit. As you could see, Glueballs are narrower than a highly excited QQR state. And so the mass over here is tantalizingly close to that of a Glueball pi molecule. And so for small energy, binding energy, as I argued, one would have this state build out of pions and the Glueball. So if you try to do a duck test on it, and that's the Wikipedia definition of a duck test, if it looks like a duck, swims like a duck, quacks like a duck, then it's probably a duck. So this state has the mass that is similar to what we derive to be a Glueball molecule mass. It is narrower than the usual QQ bar state, so maybe it is indeed a state whose wave function has a large component of a Glueball molecule. So to conclude, Glueballs are expected to be here from QCD. In large NC arguments, we expect that those states would have smaller widths compared to QQ bar states. There are possible large mixing with the highly excited QQ bar states, and we might expect unusually long-lived highly excited states. So in this talk, I proposed a new mechanism for Glueball hadronization that explains why we don't see pure Glueballs. It's not just a mixing between the QQ bar states and the Glueball state, but also possible molecular excitations. So it has direct implementations for the N-star program at JLab, and also opens up new opportunities in identifying gluon degrees of freedom of ordinary mesons. So in particular, one of the interesting conclusions from this is that the X3872 might actually have a component in its wave function that does not contain any charm quarks. And the same can be said for some newly discovered pentaquark state. That's it. Thank you very much.
Yeah, thank you very much for this interesting talk. Other questions? Christoph.
Hi, Alexei. Thank you very much for this excellent talk and sharing this intriguing idea.
Hi,
but
yeah.
I'm a little skeptical, though. And let me try to express my skepticism. Well, you might have expected that anyway, right? Well, first of all, if you want to get numbers into what you say the Glueball is narrow, we can just look at the width of the F0 1710. And this is, what is it, 123 MeV, I just checked. So that's usually a very common QQ bar width, I would say, right? So it's the order of the magnitude of the row width. Therefore, it's not that narrow after all. Well, the first thing I'd like to comment on is this X3872 analogy. if you want to say there is no CC bar in the wave functions, then you have to explain why all decay channels of the X3872 contain a charm and an anti-charm, and there's no single decay observed that does not contain a charm and an anti-charm, right?
Christoph, I did not say that that the X3872 does not contain charm anti-charm state. What I said exactly is that there might be a component of the wave function that does not have a CC bar in there. That's a very different statement.
No, that's a very different statement, and I just got you wrong, and then thanks for the clarification. But now my most direct skepticism comes from knowing the chiral structure of QCD. Clearly, pion scattering of heavy sources is universal. Clearly, what is not universal is the strength parameters at higher orders. The leading order is fixed. It's just the Weinberg-Tomasawa term. It's 1/f pi², full stop. Right, but this doesn't apply here because there aren't any quarks in the glue ball. Therefore, it's only subleading terms that contribute from the chiral perturbation series point of view at leading order. Now, let me try to highlight some analogy. We know about states resonances that emerge from non-perturbative pion heavy source interactions, but we've observed the following patterns. Those seem to only appear if the leading interaction, namely the Weinberg-Tomasawa, is operative. Examples are, say, the D0, the lightest D0 state, in which is a broad resonance, which comes from most naturally from these pi d interactions. We have KD interactions that generate these sub S2317. We just have we have a beautiful SU3 structure here. In the nucleon sector, the S111535 also is a candidate for a pi d dynamically generated object, although the eta plays a role. But these are all terms where the leading interaction plays a role. I don't know of a single example where the subleading terms generate poles, but this is what you would need here.
Christoph, I don't I mean, I'm not gonna argue about anything what you said. I mean, what you said is absolutely correct. I mean, I found I mean, I did an explicit calculation within a given model, which is rather accepted accepted model for the Glueball meson interactions. I haven't invented anything else. I just used the model which is already tuned to the spectrum of Glueballs and QQ bar states, just to show that there is, in fact, you know, from the solution of from the resummation, if you will, bubble graphs, that there appears to be a pole in the transition amplitude. That's just that. I mean, and everything.
I'm almost done with questions, but the page that you have here is already the one that I want to ask for next. This M0 square parameter in your lambda, is that what is that? Is that the pion mass, or is this
No, M0 is just a parameter of the interaction that was introduced to couple Glueballs and then QQ bar states. It's all on this paper. It's all fit to experiment. Trying to get the Glueball component of the F states.
Yeah, but then I'm confused because chiral symmetry tells me that in the chiral limit for vanishing quark masses and
it works out. Trust me,
pions must decouple exactly.
Yes.
Where do I see this in this term?
It's all described in here. I mean, I just didn't want to rewrite, you know, the page from their paper. It's all worked out. I mean,
okay,
Rishke tuned that model rather beautifully.
Okay, then I will check this.
Yes.
My final question is about, you say I necessarily get this bound state, but you know the deuteron is fine-tuned.
Yes.
Right. Therefore, that the deuteron is bound by several MeV is nothing you can predict. That's something you can observe. And then the parameter you call lambda r is tuned to reproduce the binding energy. Therefore, that there is a several MeV binding energy is nothing you can predict. But the way you formulate it is you automatically get the several MeV bound states. This I didn't understand.
No, so I'm not saying that this is exactly the same situation as a deuteron. That is to say, I don't argue that there is a large scattering length. I'm just arguing that, you know, from the calculation, this is what I get. I mean, it's It's
Yeah,
not
but
as
how
fine-tuned
can you
as
predict your lambda r? I don't understand this because
well,
it's
okay,
just
so
a free parameter.
So lambda r, right? I mean, lambda r is really is a combination. So of course it's renormalized, right? So in that case, one. So let me work out in a separate way, in a sort of in a way that is exactly how this is done in case of similar cases to the deuteron, right? So I find the binding energy, right? And so if I assume that pi 1800, for instance, is mainly molecular state, I can fit this this constant from
Okay.
the experiment, right? So since it is universal, as you say, for the whole octet, SU3 octet, I can use this result that I get from the pi 1900 to predict a K Glueball molecule, for instance. So that's
okay, this I understand now. Thank you very much. That's it.
Okay, we have another question. Maybe Bernard, short question.
Yeah, hi. Thanks for the interesting ideas. I was just wondering, I mean, just to second Christoph's message on the F0 1710, the pi 1800 is not narrow at all, right? It has, I mean, Compass measured it to be 220 MeV. So
no, I'm not saying
such a
it's
narrow
narrow.
beast, right?
I agree with you. This is just a statement from Paul Eugenio that it's rather narrow. It's not narrow.
Well,
right?
I mean, these are the numbers. But I was wondering, there are, I mean, lattice QCD predictions and also models containing constituent gluons that predict the hybrid state with 0 minus plus quantum numbers at about this mass. So I mean, you mentioned that as well. I was wondering, what would be the experimental signature that you predict to distinguish whether the pi 1800 is a hybrid or a Glueball meson molecule?
Right. So first of all, you cannot say it's either or, right? I mean, since those states are, you know, those states are rather big in terms of, you know, size. There is a lot of mixing going on between different components. So I think that the molecular state is rather different from the hybrid state. In such that the decays of that molecular component are determined by the decays of a Glueball state, of the Glueball part. So in particular, if you know, and I cannot claim it as yet, but if I claim that the molecular state represents the major part of the wave function, I can actually predict the ratios of widths of this decay into F0 980 and F0. Let me come back here. And F0 1370. So I can actually predict the various decay widths, the ratios of decay widths between of pi and 1800 into, say, F0 980, F0 1370, and F0 1500. So
okay,
they're basically following from how much of the Glueball component those states have.
That would be very interesting, because
Absolutely.
just to let you know, Compass in a Fried isobar analysis did not see the decay to F0 1370.
That would be an interesting thing to see. Yes,
you won't be aware of that, so that could be an interesting signature.
Excellent, thank you.
Okay, thank you very much. So we switch to the next presentation. Thank you very much, Alexei. The next presentation